Yeah, a lot of excitement, Brady, a lot of excitement. Because particle physics is still in the game, it hasn't died.
It's amazing, isn't it? It's a bit like waiting for buses. I was thinking about this the other day, you know, you're waiting for a bus, and then all of a sudden 3 come along at once.
Yeah, we were all worried there was no new particle physics to be found, there was no new particles, we'd found everything that was going to be found.
Well, we're waiting for a new particle, and then all of a sudden the BBC announces at least 2.
There are sort of tantalising hints of some really exciting new physics from 2 experiments, recent sort of announcements from 2 experiments.
One of them's at CERN. It's the LHC-B experiment, and you might recall we've been to the LHC and we saw the Atlas detector and we saw the CMS detector. They're called general purpose detectors, these huge fantastic pieces of kit which discovered the Higgs. There are 2 more key detectors on the LHC ring. One is called ALICE, but there's another one, LHC-B.
So the real excitement is coming from the experiment coming from Fermilab, where they've been looking at the magnetic moment of the muon.
LHC-B is a high precision detector that's looking for very fine events that might not occur very often, but by searching in particular for particular types of decay, then they've got a way of testing the standard model of particle physics very accurately. And it's through there that this potential new discovery has emerged. What they did was, if you remember, at the LHC, they fire protons around in opposite directions and then they collide them. And they collide them here in the LHC-B detector. They're looking for the decay of a particular type of meson. A meson is a combination of 2 quarks, a quark and an antiquark. And they're looking for a meson called a B meson, which has got a B quark in it. We've got these 3 generations of quarks, and the B meson, also called the bottom or beauty, is the B quark is often associated with the top quark. You and I are made up of the up and down quarks. In fact, everywhere around us here, everything around here is made up of up and down quarks. So these B quarks are very rare, and they decay rapidly. They form in these mesons, and they decay such that when they decay to another quark, which is called an S quark. This is what the particular root they're looking for, a strange quark. And as they do so, they decay producing 2 leptons. What are the leptons are what you and I are made of. Electron is an example of a lepton. But there's another key lepton called the muon. And the muon is going to be the star of the show. In particular, the number of times the B quark decays either into electrons and a positron, or muons and its antiparticle. And the key thing that it's trying to measure here is the relative distribution of these. Like, how many times does this process, the decay of this B meson, go into the electrons compared to how many times does it go into the muons? And there's a very important principle from the standard model called lepton universality. And just this idea of universality suggests that there's a common theme between the various leptons. And in fact, the belief is that you should produce electrons just as often as you produce the muons, so that if you can detect enough of these decays, then you'll find half of them the time they're electrons and half of the time they're muons. Well, about a decade or so ago, there were experiments which suggested this wasn't quite working out, that actually they were producing muons at a slower rate than they were producing the electrons, whereas you would have expected them to be at the same rate. And so what they have done, this quite remarkable team of working at the LHC-B, is they've been assembling data from 2012, in fact I think maybe even earlier, but certainly 2012 onwards, looking at all the decays of these B mesons into what are called K mesons, but basically it's the bottom quark decay or the beauty quark decaying to the strange, and looking at the output in terms of number of electrons and number of muons.
You would expect in certain processes that you would decay just as equally into electrons as you would into muons. There's no preference there, because the couplings are the same. Everything's just working at the same strength. But that's not what seems to be happening. There seems to be a preference for electrons.
The ratio of the number of times you decay to the muon divided by the number of times you decay to the electron isn't 1, but it's about 0.8. So it's decaying to the muon far less often than it's decaying to the electron. And an interpretation of that is that maybe there's another particle playing a role in this that we haven't detected, that's played no major role in anything else we've seen, but it's actually stopping the muon somehow from it decaying to the muon. It's allowing the electron route to go through, but somehow it's stopping the muon. And so there's been a lot of work on this type of thing for many years. And there's a number of particles out there which have been suggested as possible ways of explaining this. And probably the most common one that people have thought of is called a leptoquark. Leptons and quarks we usually think of as totally separate particles, but a leptoquark kind of is a new particle which brings them together, and it has properties of both leptons and quarks. So it can feel the strong force as well as just feeling the weak force and the electromagnetism force that the quarks, the leptons feel. And so I think there's going to be a lot of interest in the possibility that this process is now taking place, that there's this new particle existing for a very short period of time that then decays into quarks and leptons, and it's in such a way that it's preventing the beauty quark from decaying into the muon as often as it decays into the electron.
Why does it have to be a particle? Why can't it just be that nature favours the electron route or something like that?
It's a very good question, and in fact the standard model seems to suggest that it should go evenly in both directions. So if it's favouring one, clearly favouring one over the other, we're assuming that the experiment is correct and is picking up all the muons that are being created, then it's hard to do it within the standard model itself. So then what do you do? And it's just that the easiest thing to try and come up with is another particle. One thing I should mention is, perhaps gets a little bit technical, but it's a boson. We have our fermions, the stuff that you and I are made of. The matter in the universe is made up of fermions, things with spin half. But these are effectively bosons, which are our force carriers. So the photon has a spin 1, the graviton has a spin 2. And this has got an integer spin, it's a boson, and so it actually also acts as a force. So it could be that this is, in the news you might have heard, they talk about a fifth force, and this is acting as that fifth force. But it's hard to reconcile it simply within the standard model, and so you have to come up with something. And if you've got your favourite candidate that you can think of that might be some fluid, or then bring it to the table. In fact, there are many candidates. I mentioned the leptoquarks. Some people think of a particle called a Z prime particle. This is just the Z particle, but very massive Z particle. And then there's another called vector quarks, which are sort of, there's a whole series of them. So the second boss that came round is also quite remarkable. I mean, this is the G-2 muon experiment.
So what the muon is like the electron's heavier cousin. It's essentially very like the electron in every sense, but it's heavier. It's about 200 times heavier than the electron. And just like the electron, it has what's called a magnetic moment. This basically just it's a little bit of sort of intrinsic magnetism.
Before we describe it, let me just give you a little bit of background of this experiment, which is a ring, basically, which is 50 feet across, 15 meters. It was initially performed at the Brookhaven National Laboratory on Long Island. And then once they'd finished and done its experiment, they decided, the people who were involved in it, decided they would like to upgrade it and also take it to somewhere where there's a better source of muons. But to get it from Long Island to Fermilab, which is in Batavia, Illinois, rather than going sort of across land, it went out down the North Atlantic, down to sort of New Orleans, up through the Mississippi River, into the Illinois River, and then got put on around Chicago area, got put on a huge lorry and got taken up the highway to Fermilab. What this experiment does is, again, it looks at the muon.
If you didn't have sort of, all the corrections coming from quantum field theory, things like that, then the magnetic moment of the muon, like the electron, it would be 2. It would just be the number 2. That's related to the fact that it has spin 1/2. But the answer is not exactly 2. Okay, it's slightly bigger than 2. The magnetic moment of the muon is slightly bigger than 2. And the reason it's slightly bigger is it comes from sort of quantum corrections to that number. So what happens is the muon, it can sort of shapeshift.
And the muon is a particle that's got a charge, and so it's got a dipole, which means it acts like a little dipole magnet, a bar magnet. And if you move that muon in a circle in a magnetic field, it will begin to wobble, a bit like a spinning top. You know, if you push a spinning top down and let it go around, it doesn't keep at the same height. It sort of wobbles as it goes around. And you can measure the frequency of this wobble. Now, the frequency of this wobble tells you about the strength of the magnet that the dipole is. It's called the magnetic moment of the dipole. So this is what's being measured, okay? And the strength of this dipole.
It can give off a photon and then reabsorb it, and this will create a correction to the predicted value for the magnetic moment. That photon itself can sort of shapeshift into an electron-positron pair that can then be created and annihilate, become another photon which gets reabsorbed. There are all these sort of quantum corrections, this cloud of quantum corrections that can affect the value for the magnetic moment.
But then people sort of naturally said, well, it's not just electrons and quantum electrodynamics that could be important. Maybe W and Z bosons might be important. Maybe they're popping in and out of existence as well. And so they started doing calculations based on what's called the vacuum fluctuations of these particles. And they modified this number. It still was 2.00223, but you had more digits added on. And everything was fine until you reached the 7th digit, the 7th decimal place, because at that point, you have to start including the effects of quantum chromodynamics, the quarks that can exist. And they're formed by the electron or the muon. It could be any of these leptons, and the muon being much heavier is one that is worth probing because it can create these extra particles around it in the vacuum fluctuations. The muon can lead to a photon will emerge, a virtual photon, then decay, and then from it comes a quark-antiquark pair, which then reconnect to a photon, and then it gets reabsorbed by the muon. That's the process. But this quark-antiquark pair you have to be able to account for, and that's where the problem is.
What we found in 2001 was that the theoretical expectation for the magnetic moment was different to the observed prediction. They disagreed at the 8th decimal place. Okay, so the 8th decimal place, when you're really starting to probe these rare processes, the numbers differed. And so people at the time got very excited about this, but of course it wasn't statistically significant then. I think it was around a sort of 3 sigma results, okay? And then, you know, so people, not quite enough to class as a genuine discovery in particle physics, but enough to get people excited.
So the theory now is to try and calculate that. And there are 2 approaches to these calculations. For the quarks, they're called the virtual hadron processes, and they differ. Now, one of them differs in a way which is consistent with the observation of this experiment, which I'll now describe, and the other differs in a way which leaves it inconsistent. So their value for G is different to the experimental value by 4.2 sigma. And if you recall, 5 sigma difference between a theory and an experimental value would be a discovery.
4.2 is pretty good,
It's
though.
getting close, isn't it? The experiment is this 50 feet, or 15 meters, for our European colleagues, ring. So at Fermilab, they can produce high-energy muons. They fire them into the ring, and they go around in a big magnetic field. And if you recall, I said that because they've got a magnetic dipole, they begin to wobble. A muon's heavier, 200 times heavier than an electron. Otherwise, pretty much identical. It doesn't want to stay there. It lives for about a millionth of a second, by which time it's circled around about a few hundred times, but it then decays to an electron. It produces an electron. And the electron gets detected in the detectors surrounding the ring. And the muons are carrying on, going around and decaying, and by looking at the energy of the electron that comes out and the direction that it comes into the detector, you know about the wobble. And the wobble, if you recall...
The wobble of its sort of parent muon.
Yes, exactly. And that wobble tells me directly about the muon magnetic moment, this G that we're trying to get.
It's very hard to calculate these sort of hadronic contributions to the magnetic moment of the muon. It's very difficult to calculate. But people got better at doing the calculations. They started to zoom in on an agreed value for the sort of standard prediction. And then, of course, we needed a better experiment that could really pin down what the observational result was.
And they've done this now they've been doing this experiment for the past, I don't know, five, 6 years. And they've now started releasing their data. They've released the first 6% of their data. The key thing they're trying to do, of course, is control the errors, reduce the systematics, make sure they understand. And sadly, I can't do that justice. But that's a remarkable achievement that they've done.
So the theory seems to have tightened up a bit, but also the experiment has now tightened up as well. And now we've got over a 4 sigma result, which again is still not quite enough for it to class as a particle physics discovery. But it's really starting to get interesting now, and it does seem that it's sensitive to new physics.
It was all done blinded, so that when they released the data, all of the team saw it for the first time. There was a key thing, a key frequency clock, which they didn't know about, and that they were given that information. That then allowed them to plug it into a key formula to get what G is. And they found the number G that they got was the same as the number that they'd got at the Brooklyn National Laboratory. And if you remember what I've just said, that is 4.2 sigma away from the theoretical prediction that came from this international group of physicists who were working on the theory behind it. And so there was this remarkable result that's emerged that suggests, if it holds, that the theory is based on standard model physics. The experiment is the experiment. You just do the measurement. And it's once again suggesting that there's something else happening, that the muons are being tilted a bit more because actually the theory result is smaller. The value of G from theory is smaller than the value of G from the experiment. And so it means the magnetic effect is larger in the experiment. So whatever is causing this change, if it is new physics, is causing the muon to have a slightly larger internal magnetic field than it otherwise would. And leptoquarks and other possible candidates are out there.
Let me see if I've understood this correctly. It sounds to me like in nature, in physics, there are particles popping into and out of existence spontaneously all the time, like a sort of a soup.
Yes.
And one way to detect that soup, to measure what's in it, what vegetables and carrots and sprouts and things are in it, is to look at how that soup affects muons. And so they've been doing really, really good experiments with muons to see how they're being affected as they travel through this soup, to get a better and better idea of what's in the soup.
Perfect.
And now that they're getting these measurements better and better...
There's a new vegetable that they've never seen before.
Absolutely. There's this quantum soup that surrounds all the particles. Now you can imagine taking the particle out of the soup, right? And that's what we do with our first approximation in our calculations. We take the particle out of the soup, we do the calculation, we make a prediction. Okay, but then we start putting the particle in the soup, right? And we see that the soup starts to affect our results. And absolutely, you're right. If there's some sort of, I don't know, alpha spaghetti floating around in there or something, it's going to affect your results. And muons, indeed, because they're heavier, they're more sensitive to that unexpected, unknown physics that could be out there than, say, the electron would have been.
This is a really interesting time. First of all, it's worth pointing out at the beginning I mentioned this high precision experiments. These deviations between the experiment and the theoretical predictions are in the 8th decimal place of the calculation. And also, there is another group. I said there were these 2 theory groups approaching this problem. The theory group that the experimental group have aligned with, in the sense of comparing their results directly with, have had to incorporate experimental data into their analysis. Not the experiment of the G-2, but other experimental data to deal with this hadron question, the vacuum polarization of the hadrons. And they're the ones that have come out with the very low number, 4.2 sigma away.
We maybe shouldn't get ahead of ourselves. It might not be a new particle, right? So what it could be is it could be that the theory prediction is still not right. And it's a really unusual state of affairs now. We actually have, there's been a rival paper which is claimed to have done the theory calculation in a different way and gets a result that's more in line with just with standard model physics, nothing fancy, but which is more in line with the observed value.
There is another group of people, a smaller group, but that have just simply used QCD on a supercomputer. They've just looked at Euclidean lattice QCD, it's called, worked on a supercomputer, no experimental input, using the standard model, and they have come out with a result which is actually compatible with the experiment. Okay? And so we are in this amazing situation where we have the two theory approaches. This shows you that science is not a single track to get to somewhere. These two theory approaches, both trying to solve a problem, are coming in with numbers which are inconsistent with each other. One of them is consistent with the experiment, which was consistent with the original experiment, so it suggests the experiment is okay, right? If these two are consistent 20 years apart.
Sort of accepted result, the one that we're saying is different to the observation. What they do is they take a sort of data-driven approach. They're worried about the effect of these hadrons in the quantum soup, right? So those are very difficult to calculate. Hadrons, they're strongly coupled, they're all tied in with gluons in this sort of gluey mesh. It's difficult. Quarks are a pain to deal with, right? So this is difficult. So rather than actually try to calculate that because it's too hard, they take input from other experiments, so it's a data-driven approach. Say, well, given what that experiment's showing, this probably suggests that this value of this thing is about this, therefore we'll calculate the rest. Then they get an answer for the magnetic moment of the muon that doesn't agree with experiments. But the other guys are this BMW collaboration, they're called, right? Nothing to do with the car. It's named after Budapest, Marseille, and Wutapal, I think the name of the city is. So this BMW collaboration, what they've done is they've shoved everything into a computer, a really fancy, spanking supercomputer that literally puts all those quarks and hadrons on a giant lattice and does the brute force calculation, right? Really, really sophisticated, something that you could never have done decades ago, really powerful calculation. And they've done, and so they've done this calculation, they're getting something more in line.
Why don't we just think that the first group are the one that got it right? That seems like the more obvious solution.
Yes, I mean, and quite a few people think this may turn out to be correct, which would be in some ways sad if you're really looking for new physics, which we know has to be there somewhere. We still don't know why we're surrounded by matter and not antimatter. We don't know what the dark matter is. We need some new physics.
It's entirely possible that there's some sort of systematics that aren't quite right in the lattice calculation, in the BMW calculation, but maybe not. It's a really, really impressive calculation that those guys have done. Or maybe the data-driven calculation isn't right. But even if the data-driven calculation isn't right, there's something going on here because they're using data. So it's like, is there something we're not understanding about that part of the data and how we feed it into this calculation? It still smells that there's something we're not understanding about fundamental physics here. So either way, whoever's right about the prediction here, there's something going on that we don't understand. It might not be the magnetic moment experiment that's we're missing, but it might be something else.
I think the fact that we're seeing something at the LHCb, this muon, this decay of the beauty quark to muons, far less than it goes to electrons. And then this G-2, also involving the muons, is suggesting there's something going on. The muons, the heavier leptons, are being affected by something. And so I'd like to waver on the side of saying there's something there.
I think it's new physics. I really do. So the reason, I mean, look, there are other reasons to expect new physics to be just around the corner. You know, we talk about why is the Higgs particle so light? This is a mystery that we don't understand. Why is the Higgs particle so light? New physics can explain it. You know, there's things like, what is dark matter? You know, we know dark matter's out there. We need a particle to explain it. Where is it? Okay. There's another sort of quirk, which is that we like to think that all the different coupling strengths of particle physics will come together and unify at some high energies. And you need new physics to make that happen. So this beautiful elegance. So there's lots of reasons to expect that new physics is just around the corner. It's why we built the LHC, for example, right? So the fact that now, and this is why everyone was freaking out, because it was like, it didn't seem like there was any. No experiment was showing anything up, except for this. And this is finally pushing us in that direction that maybe there is something there. You just had to look in the right place, and that's really exciting.
The day after this announcement of G-2, 30 papers appeared on the archive. Another 13 today. That paper, the PRL that has appeared, already has 36 citations after 2 days. It's just going through the roof.
Now, of course, there'll be 1,000 papers, well, I'm exaggerating, but there'll be a lot of papers come out in the next few days, people ambulance chasing, explaining what explains this new phenomena. I mean, I was chatting to some collaborators yesterday, right? And we weren't thinking about the Muon experiment, the Muon experiments at all. We were just thinking about trying to explain dark energy and string theory. And then we had this particle in it that I was a bit worried about how light this particle was and what it might affect. And we did some digging while we were on Teams. Obviously, everyone's on Teams, aren't they? And we actually came across a constraint based on muon magnetic moments, and I was like, well, this could be it, you know, sort of joking, right? But you never know.
These two announcements have obviously made a real celebrity of the muon, which is a particle that doesn't get a lot of love. No. I don't know much about muons.
I like the muon. Why are you being harsh on the muon for? I think it's great.
You make it sound like they're really unstable. Are there muons in this room on a permanent basis, or are they kind of a sort of a transient visitor?
They'll be, if they're there, they'll just be transient. Yeah, they're certainly not here sort of on a permanent basis. And they were first detected via cosmic rays. You know, the cosmic rays is this, we need to do something on cosmic rays, by the way. But the cosmic rays, the highest energy particles we've got, hit the atmosphere and produce all fundamental particles that are consistent with E equals mc squared. And the muon is one of them. It decays in about 1/1000 of a second. So if they're popping up here, they're decaying very rapidly.
Do you get jealous that the experimentalists seem to get all the headlines and the big moments and the big stories?
I'll behave. I mean, like, look, the superstars of physics are all theorists, right? Of course they are. That's without question. So no. I mean, come on, Einstein, Newton, all these superstars, they're all theorists, aren't they? Experimentalists are just the Oompa Loompas. Don't say that, don't put that in.
Allows you then to read off where the particles have come from. The particles aren't affected. They then move out to a second set of detectors called the calorimeters. And the calorimeters actually stop the particles.